Okay. So in this lecture, we'll see the main methods used to generate electricity from wind. Basically, they are topologies, 5 different topologies through which electricity is generated from wind. So how to harness wind power? Different topologies. Okay, so the first one is turbine driving a DC generator. Let's see how the topology is. It will be like this. So these are the blades. Now let's mark this as number 3. Each component I am numbering. So from here it will so this is a DC generator. This is connected to DC load. So this is DC load, which is number 6. This is number 5. This is number 4. This is number 3. And here I have the tower, which is number 2. And this is the turbine itself, blades number 1. So simple windmill supported on a tall mast, that is what is shown. So number 2 is the tall mast, then that drives a DC generator, which is number 4. Then the gearbox is shown as number 3. Okay, then which multiplies the speed of the windmill 20 or 30 times, maybe up to 50 times also, because we know that the speed of the blade is much less than the speed of the generator rotor. So there should be a scaling up of speed happening there. Which permits the use of a relatively small generator. So the generator would be small, and if that is the case, then 20 or 30 times the speed of the blade would be the generator speed. Now the energy delivered by the generator is stored in a battery, which is number 5. This one, number 5, stored in a battery. And the battery acts as a continuous and reliable source of power for the DC load. Now the loads may consist of a few 12-volt lamps and a DC to AC converter to power AC loads. So the loads can be of DC itself, that can be the DC 12-volt lamps, or AC loads can be powered through DC to AC converter, like a TV set or something else. Then such wind-driven DC generators are only used in remote locations. This is normally used in remote locations. See, this is not the one which we normally see in wind power plants or windmills in India, which are normally large scale. It can be up to 2 megawatts wind turbines, from 600 kilowatts to maybe 450 to 600 to up to 2 megawatts, 2 to 2.2 megawatts wind turbines. But these small generators here, these small DC generators, their capacity is limited to a few hundred watts. That's all. 100 watts. It's not 100 watts, a few hundred watts. A few hundred watts. So this is what is one of the topologies. Now we move on to the second topology. The second topology is turbine driving an asynchronous generator at constant speed. What is this? A turbine driving an asynchronous generator at constant speed. What is an asynchronous generator? An asynchronous generator is an induction generator, right? And constant speed in the sense, this is normally squirrel cage induction generator. So similar to what we have drawn for DC, I'm going to draw here for AC also, induction generator also. So I have the, okay, so again, this first I'll draw the blocks, then I'll move on to, so this is the gearbox, then this goes like this, and this is my induction generator. Then I have three-phase power generated from the induction generator, and I have capacitor banks to support reactive power like this. Okay, now this is my transformer, again three-phase output connected to the grid. So grid I am representing like this. Grid I am representing by infinity. Okay, so now I'm going to number it. This is number 7. This is number 6. This is number 5. Then this is number 4. This is number 3. This is number 2. And this is number 1. Okay, so the same thing. We'll explain each component with reference to the numbers. So these are large commercial wind turbines. Normally this topology is used in large commercial wind turbines that drives a squirrel cage induction generator, which is number 4 here, by means of a gearbox, which is number 3. Then the stator of the generator here, the stator of the generator is, here I'll mark like this. The stator of the generator is connected to the power grid through what? Now that is number 7. Okay, power grid is number 7. Power grid is number 7. Power grid of the electric utility company by means of a step-up transformer, which is marked as 6 here. Step-up transformer. So the magnetic flux in the stator rotates. The magnetic flux in the stator of the induction generator rotates at synchronous speed corresponding to the grid frequency. So what produces the magnetic flux in the induction generator is the grid supply, the supply from the grid. Okay, so the speed of that magnetic flux will depend on the frequency of the grid supply, the power supply from the grid. Now the rotor of the induction generator, it rotates faster than the magnetic flux, which is rotating in the synchronous speed. So this F is F grid. This F grid governs the speed of magnetic flux, which is NS, synchronous speed. Okay. Now I have a rotor here whose speed is NR, and NR is greater than NS. That is why it is in the generating mode. It is in the generating mode. When NS is less than NR, it is in the motoring mode normally. Motoring mode. But here we know that our purpose is to generate electricity. So this induction machine is operating in the generating mode where rotor speed is greater than the synchronous speed of the flux. Okay. Now the turbine runs at essentially constant speed, because we know that here some 1:60 or 70 would be the ratio. So 60 times the speed of blade would be the speed of induction generator. So for small variations in speed for the generator rotor, it won't affect the turbine. Right, it won't affect the turbine, even though there is a load change or the power that is imported to the grid. If that is changed, the rotor speed may be affected, but a very low proportion of that is only reflected on the turbine, because the ratio is 1:60. I mean, here in this example it is 1:60. So essentially it's a constant speed turbine. Now, because of this constant speed, the turbine cannot extract the maximum amount of energy in the wind at all times, because the range of speed for the induction machine is very small range of speed for the induction machine. Okay, and essentially the blade speed is constant speed blade, turbine blade. So according to the wind speed, the turbine is not moving faster. That is not happening. Okay, faster in the sense considerable speed change is not there. Now, because of this, the problem here is it cannot extract the maximum amount of energy in the wind at all times. Accordingly, the speed should change, otherwise that is not happening. Now, the reactive power absorbed by the generator, because to produce magnetic flux, it depends on the grid supply, right? To produce magnetic flux, induction generator depends on grid, right? So essentially it should extract reactive power from the grid, Q from the grid. Q grid would supply the machine. But to avoid this, if many wind turbines are connected and if all the wind turbines are depending on the grid for reactive power, then it may affect the voltage profile of the entire grid itself. So to avoid that, we locally support reactive power using capacitor banks, which is number 5. Capacitor banks, which is number 5. So here the power delivered to the grid is close to unity power factor. It is made close to unity power factor by use of the capacitor bank. Let the active power developed by the turbine be PT. This is transmitted to the electric utility grid. This is transmitted to the grid. Minus PT minus. What are the losses here? In the gearbox there is a loss, right? Then where else? Generator there is a loss, transformer there is a loss. So subtracting these losses from PT, the remaining will only go to the grid. Okay. And the power of asynchronous generators is typically 100 kilowatts to 800 kilowatts. Okay, 100 kilowatts to 800 kilowatts. Now, some asynchronous generators are equipped with two stator windings. Here, suppose there is only a single stator winding. Some other topologies are there where two stator windings are possible. So we can make use of two poles. Operation with two number of poles. One can be 4-pole, another can be 6-pole. So what is the advantage? When the wind speed is high, the lower number of pole is used because it corresponds to a higher generator speed. What is NS synchronous speed is 120 F by P. F is the frequency. Here F is grid frequency. Okay, P is number of poles. P is number of poles. So if you want higher speed, you need to take lower number of poles, right? So when the wind speed is high, you can use 4-pole mode. When the wind speed is low, you can use 6-pole mode. Okay, if you have two options of if you have two stator windings in the machine. So such a topology is also there. Okay, so that is the second one. Now the third one is turbine driving an asynchronous generator at variable speed. The third one is the turbine driving an asynchronous generator at variable speed. What is this? Here let me draw the topology. It is like this. Again the same thing. This is the gearbox. Same thing here also. This is the machine. Okay, this is the machine. See, to show the three-phase winding, I am drawing three concentric circles and three-phase supply. This is going to a converter. Converter 1. Then I have here something like this. Then I have another converter, which is converter 2. Again three-phase. Transformer. Again this is going to grid. So this is grid. I'm representing grid by infinity, denoting by infinity. So now I'll number it. This is number 8. This is number 7. Then this is number 6. This is number 5. This is number 4. This is number 3. This is number 2. And this is number 1. Okay. So here, what is the difference compared to the earlier one, the previous one? Compared to the previous one, here also we use a squirrel cage induction generator, but it is connected to a converter, which is number 5, that generates a variable frequency. So this generates a variable frequency. This one generates variable frequency. As a result, the synchronous speed of the generator can be varied. This one, the synchronous speed of the generator can be varied, because earlier the synchronous generator was directly connected to the grid. Now it is connected through a power electronic interface which can produce variable frequency. So in the previous case, the synchronous speed of the flux in the induction generator was completely governed by the grid frequency. Here the grid frequency could be varied with the help of this power electronic interface. So accordingly, this NS could be varied. So that is the main difference when compared to the previous one. So this synchronous speed is varied according to the speed of wind. So let this be speed of wind. Then according to the speed of wind, this is varied. What the frequency is varied. Accordingly, the NS is varied. So the wind speed could be captured by an anemometer and in such a way as to extract the maximum amount of available energy. So this NS is varied. This NS is varied such that maximum amount of energy is extracted from the available wind speed. So in effect, by imposing an optimal speed on the induction generator, we automatically impose the optimal speed on the wind turbine. That is what we do. Now, what about this converter 5? This one is converter 5. Okay, converter 1. So the converter 1 absorbs the active power PT. Let this be PT, which is coming as output from the induction generator, and at the same time it furnishes the reactive power drawn by the generator. It furnishes the reactive power drawn by the generator. So reactive power direction is this, active power direction is this. Okay, so it supplies the reactive power also, because here we don't have capacitor bank. Instead of that, that responsibility is taken up by the power electronic interface, which is this converter 1 and converter 2. Now the constant DC link voltage here, the constant DC link voltage here, and the converter 6, this one, the converter 6 carries the active power to the converter. So here it carries the active power to the converter, and from here again to the grid. So this is active power to the grid, active power to the grid. Okay. Now converter 2 converts this to 3-phase at a standard frequency, whether it is 60 or 50 hertz, whatever. So that will be done by converter 2, and then to the electric utility grid. Okay. So here each converter must carry the full power delivered by the generator. No doubt in that. In terms of power, it will carry the full power. Then some converters generate sinusoidal pulse width modulated PWM voltages, which prevent undesirable harmonics from reaching the generator and the power grid. So basically what we need is harmonics should be avoided here as well as here. We don't need that. So in between we should do whatever possible to remove it. Okay, so that is one thing. Now comes the last topology. This is the fourth one. What is this? This is doubly fed induction generator, turbine driving a doubly fed induction generator. Okay, again I will draw the figure. So this is my blade, then here again the same thing. Okay, then this is connected to the gearbox. It is like this. This is my machine, the generating machine. Okay, now here there is a difference. So I have one connection from the rotor, which I am taking like this. Okay, taking like this. This is going to a converter, which is converter 1. Again a DC link here, then it's going to another converter, converter 2. Output is 3-phase. It's going to a transformer, going to the grid, Now you know that this connection is from the rotor. Okay, rotor of the machine. Here I have another connection from the stator, which is going to, this is going to the output terminals of the converter here. Like this. Okay, so this is ES, which comes from the stator. This is ES. Electrically, they are the same points. Okay, so now the stator only produces the magnetic field. So frequency is important here, F, and this is the electrical power, PE. Okay, now this is ER, rotor voltage. This is another frequency, F2. Okay, this is PR. Okay, PR. Now let's mark it 5, 6, 7, 8, 4, 3, 2, 1. Okay, so here this shows a wind turbine driving a wound rotor induction generator, which is number 4. Okay, by way of a gearbox which is number 3. Then the electric utility grid voltage EG. Where is EG? Here. The electric utility grid voltage EG is stepped down to a lower voltage ES. Where is ES? Here, ES. So this transformer steps down this to ES. What is the use of this? This ES is what is supplied to the stator here, stator of the machine. So that will govern the speed of magnetic flux. So this converter 2, which is number 6, the converter 2 transforms the line voltage ES to a constant DC voltage ED. Constant DC here, the constant DC voltage ED. So this ES is changed to ED by the converter 2 or number 6. Okay, then power can flow from AC side to DC side of this converter and vice versa. So this is basically bidirectional power flow. Here I have bidirectional power flow. This is AC to DC side and DC to AC side. Now what about converter 1? Converter 1 transforms the DC voltage ED. Here I have ED. So this is the input to converter 1. The DC voltage ED into a voltage ER. So this is my ER. So here I have ER, whose magnitude, frequency, phase shift and phase sequence can be varied according to the control, according to the desired control of the converter. So this ER, everything related to ER, magnitude, frequency, phase shift and phase sequence can be varied. So power can flow from DC side to AC side, here DC side to AC side and vice versa. So this is also bidirectional. Okay, now the stator of the wound rotor. This is the stator of the wound rotor induction generator. It is connected directly to the power line here. It is connected directly to the power line whose frequency F is, let it be 50 Hertz. This F be 50 Hertz or 60 Hertz. Consequently, the stator voltage ES, this one, the stator voltage ES and its frequency are the same as those of the line voltage, because from the line voltage we only have transformer here, right? So it is almost same as the it corresponds to the grid voltage. ES corresponds to the grid voltage. The rotor is connected to converter 1. The rotor here, the rotor is connected to converter 1. Rotor of the machine is connected to the converter 1. For what? Its 3-phase output voltage ER here, ER, the converter output, the output of converter 1 ER, and the frequency F2 can be varied by the converter control. Okay, so these are the advantages. So everything can be controlled here using the stator the stator voltage is directly coming from the grid supply, but the ER can be varied by all means. ER is the voltage at the rotor, okay, rotor terminals. It can be controlled, the phase shift, then the phase sequence, the magnitude, everything can be controlled by the converter control. So the machine is fed from two sources, ES and ER. Now the machine is, that is why it is known as doubly fed. Doubly fed. Basically this induction generator is fed from two sources, one is ES, another is ER. To the rotor, ER comes, to the stator, ES comes. So the principle of this generator is that what is the need of two different sources here? The frequency and phase sequence of the voltage ER together with the stator frequency F, that determines the speed of rotation of the machine. So basically the speed of rotation of the machine is varied. But here the stator frequency is fixed because it has no control. That comes from ES, which is just output of the transformer. There is no converter here. It is just coming from this point. So ES is not controlled, but ER is controlled completely. All the parameters of ER, magnitude, frequency, phase sequence, everything is controlled. So the speed of rotation is essentially imposed by the rotor frequency F2 here. Rotor frequency F2. As a result, the wind turbine can be forced to rotate at that optimal speed, which extracts maximum power from the wind. Maximum power from the wind. Where the wind speed is monitored by the anemometer. So according to the wind speed, we can control F2 and ER, which goes to the rotor, which controls the speed of the machine. Okay, that will control the speed of the blade, or that will accordingly extract maximum power from the wind. Okay, so that's all. These are the major topologies for wind turbines. Please go through this. Thank you.